Good morning, good afternoon, or good evening, depending on where you are, and welcome to today's DevOps.com webinar, brought to you by TechStrong and Fairwinds. My name is Cody J. Brown. I'm the host of TechStrong Learning. We have an exciting demonstration ahead, but before we begin today, I have just a couple of housekeeping notes. First off, today's session is recorded, so if you miss any of the discussion or you would just like to rewatch or share, the on-demand recording will be made available shortly after we conclude today. If you have any questions for Andy, we want you to go ahead and submit those using the Q&A tab on the right side of the screen, and feel free to use the chat tab for any other comments you'd like to put forth. We do have two polls in today's webinar, one toward the beginning and one toward the end, so your participation in those is greatly appreciated. And at the conclusion of our webinar, we will be giving away 4 $25 Amazon gift cards. So our topic today is building stability. Pitfalls of not setting Kubernetes resource requests and limits. And I'm joined today by Andy Suderman, Director of R&D and Technology at Fairwinds. Andy, once again, thank you so much for being here with us today. I'm going to give you the floor.
Awesome. Thanks for the great intro, as always. So yeah, as the title says, I'm going to talk about pitfalls of not setting your Kubernetes requests and limits right. I think we spend a lot of time talking about the fact that you should set resource requests and limits, and making it very clear that that's an important thing to do, and it's important to the stability of your clusters. But what we don't often get to see, or we don't talk about, or sometimes mystifies us when we're debugging things, is what happens when we do it wrong. So I've set up a series of demonstrations today. All of these are contained in a GitHub repo that I will share a link for in the chat and will be available. This GitHub repository is available publicly in our Fairwinds GitHub. So I'm going to drop that in the chat real quick here, just so that you all have access to it. If you want to take a look, follow along with kind of what I'm doing here, or get an idea of what, or if you want to recreate this demo on your own later on, this should give you the guide to do it. But before we go too much further, the first thing I want to do is do that first polling question that we talked about, just to get an idea of where the audience is at. So what is your greatest opportunity to improve your Kubernetes environment? Are you looking to get help with the basics, just get a general best practice assessment, improve the security posture of your clusters, improve the security posture of your, oh, that's in there twice, I'm not sure why, saving money, or improving the reliability of apps running in Kubernetes? So if you could all give that an answer. All right. Got a few results coming in here slowly. Looks like the majority of folks here are looking to improve the reliability of apps running in Kubernetes. It's a great answer because that's what we're going to talk about today mostly. I think, one of the side effects of setting resource requests and limits properly can be saving money, but the first and foremost concern is improving the reliability. All right. I think we're still moving on some of these. Probably about it. Well, thanks, y'all. Appreciate the answers. And I will keep moving on then. So I'm going to talk first a little bit about the setup of what we have going on here. So if we go back to my screen here, we're going to leave this up for most of the time. I've got a lot going on the screen, so I'm going to talk through it. I shared the link to the repository, but what we have running is a GKE cluster. It's running 1.20, 1.6. So not the newest version of Kubernetes, but a version of Kubernetes. We have a set of M2 standard 2 nodes. Those have 2 CPUs and 8 gigs of memory apiece. And node autoscaling is enabled at a setting of 1 to 2 nodes per zone. So we can get as many as 6 nodes. We can get as few as 3. So if I take a look now, do a kubectl get nodes, we see right now we have kind of a static state of 4 nodes running. And then in this cluster, we have an application. This application is in that GitHub repository. The manifests to deploy it are. It's called Yelb. And Yelp looks like this. It's just a simple voting app. It has a Redis cache, a Postgres database backend, a backend app server, and then the front end app. And so there's 4 different pods associated with running this application. The way this app works, you can go in, you can vote for where we want to go to lunch. It updates the total each time, and it keeps track of those totals over time. And that's just running on a load balancer port or on a load balancer service in GKE. We also see the number of total page views. Relatively straightforward front end, back end, multi-tiered app. Nothing too wild going on here, but it does have a certain amount of complexity to it. And like I said, that's all in the app directory here. That's just a set of raw Kubernetes YAML manifests that you can use to deploy this. So we have our Yelp app, and I have written, so one of the other tools I'm going to use today is called K6. It's a load testing tool. And I have written a script in this repository called load.js, which is a K6 load script. And I'm not going to go through all the details of that script. Essentially, what it does is it emulates me doing this: loading the page, voting, and voting. So I can run this script, and what K6 is going to do is it's going to give me some idea of the performance of my app. So I'm going to run load.js with K6. All the tools that I'm using today are linked in that GitHub repository as well, in the README at the very bottom. So if you're interested in downloading any of these, most of them, I believe, most of them are open source, and all of them are available. So we see some information, and the lines that I'm going to care about today are the HTTP request duration. So I'm just going to go straight with the average because it's easy to grab. It's 175 milliseconds on this run. If I keep running this app, running this test, I'm going to keep getting sub 200 millisecond performance. And then a total iteration should take around 6 to 7 seconds. So that was the load, click, 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 click. There's some sleeps in there. And so this is like our baseline performance. This is where we're at. This is what we expect our app to do. On the top of the screen here, what we see is the pods I was talking about. So we have our Redis server. We have 3 app server pods. This is the back end. We have our database pod, and then we have our UI pod. There's 2 replicas of that, and that's the front end. We do have a horizontal pod autoscaler in place, but it's pinned at that 3 replicas right now, just so that we're not introducing another variable into these demos that we're about to do. So that's the setup. That's what we have running in the cluster. And then I also have a little bit of load running against this app just in the background so that we're running at sort of a normal steady state for what this might look like if I was running it in production. So the first thing that we're going to talk about is what happens if you don't set any requests or limits. So I'm just going to, I have in here a demo 1 course YAML. This is just a list of Helm charts that I'm going to install. It works with another tool that we use called Reckoner. That's again listed in the repository. But I'm going to launch 2 separate sets of pods into this stress namespace, and they're going to run the Linux program stress. And one of them is going to just try and consume 2 CPUs, and one of them is going to try to consume 4 gigs of memory. And I'm going to run 8 replicas of each of those. And what I'm not going to do is set any resource requests or limits on this stress app. So I'm going to start installing that. I'm going to plot that course, that demo 1 course YAML. And then I'm going to talk a little bit more about what we have going on with this app. If you look at the YAML manifest for this application, the way it's deployed is the app server, which is what we're going to focus on primarily today. The app server has resource requests and limits specified, and it has them specified using what's called a guaranteed QoS class. That means that my requests and my limits are exactly the same. So if we look at the app deployments, so we can do this up here. If we go describe or describe the app server up here, and we look for the, oh, that's my bad. K9's a bit funky sometimes. We can look at the deployment for the app server. look at the resources block for it. And we see that it's set to a CPU request of 200 millicores, a CPU limit of 200 millicores, a memory request of 100 megabits, and then a memory limit of 100 megabits. And so this means that it gets put into the QoS class called guaranteed by Kubernetes by setting it that way. And so it's going to do its best to give it all of those resources. So I've deployed all of those pods into the stress namespace, and I have attempted to consume all of the resources everywhere, basically, by doing that. And so what we're going to see first by doing this is that our app right now doesn't seem to be affected at all. All of our pods are still running. We can run our load script. And if we check the stats on that, it should take about 6 to 7 seconds. And our average request duration should be under 200 milliseconds. That's still true. Great. Love to see that. But if we take a look in the stress namespace where I just deployed all these pods, we're going to see something much worse. We're going to see this evicted status for a bunch of pods. So if we take a look in the stress namespace and we describe one of these evicted pods, what we're going to see is it was evicted by the kubelet because the node had conditioned memory pressure. The other thing we're going to see is that we've probably attempted to scale up. 4, 5. We started with 4 nodes. We're up to 5 nodes. And if we look in Yelp here at nodes, we're going to see that our CPU usage is over 100% in many cases. And our memory usage is getting sort of high on some of these as well. And so the good news of this is that our app here is not affected. So by setting that guaranteed QoS class, I've effectively guaranteed to a degree that my application won't be affected by things being deployed in the cluster that don't have proper settings. Now, if my app had not had resource request limits, it's just as likely that this pod would have gotten evicted in the case that someone else deployed a rogue application, shall we say, kind of like I did. Obviously nobody's going to intentionally try to eat all of the memory and CPU on all the nodes. But if I'm deploying a Java app, who knows? I might accidentally try to eat all the memory on the node. So that's kind of a quick breakdown of what happens when you don't set any resource requests and limits whatsoever. So set your resource requests and limits, set them to something sane so that we don't get evicted pods, we don't get node pressure, we're not running way too many nodes and maxed out on our node count because GKE just spun out another node for us. So we're going to be, not using these nodes, but we're going to have them because of our rogue app here. So I'm going to delete that stress namespace because I think that's enough with that demonstration. Okay, another thing to think about when deciding whether or not to set resource request limits, if we don't set them at all, our horizontal pod autoscalers won't function. If we're using a CPU or memory-based horizontal pod autoscaler, it will not be able to scale that pod up and down. And the scheduler will just really put the pod wherever it wants because it can. So that's no resource requests and limits. So just a quick reminder, feel free to drop any questions you have into the Q&A. I will be watching it and trying to answer those as they come up. But we're going to let our app kind of settle back down to steady state here. Let our cluster settle back down to steady state. Hopefully it'll scale back down here shortly. And K9s will stop yelling at us about critical CPU level because we're not trying to eat all the CPU in the cluster. If we had gone and clicked on this app during the demonstration, I'm pretty sure it would have just kept working. I think that K6 demo showed that. So if we go look at our README here, we're going to move on to demo 2. So this one's really interesting and a little bit harder to kind of visualize and think about sometimes. So CPU throttling is what happens when you set CPU limits really low. And so we're really going to take a look at what happens when we do that. So what I'm going to do is I'm going to find my app server deployment and I'm going to edit that. And say I have no idea how much CPU my app needs at all. And I'm just going to set it to 10 millicores, just as low as I can, to a very, very low level. It should run, maybe I've run it locally and it doesn't seem to consume any CPU. So I'm going to drop that limit down to 10 millicores. We're going to wait for the pods to stabilize here and see what happens. You'll see that container creating takes a long time, and it may not happen at all. Because if we describe this, oh, not yet. Give it a second. Okay. Newest pod is now in a running state. And we describe it, we will start to see that the readiness and liveness probes are failing on this pod, which seems a little bit odd. Like the pod started, it seems to be running. If I look at the logs for it, we'll take a look. Interestingly enough, we're not going to see any logs whatsoever. And if we top pods in the Yelp namespace, our newest app server pod here is not showing any metrics yet. Yep. So the pod has continually failed its liveness probe, and by doing so, it failed to even start. So what's happened here is that we've throttled the CPU down so far that the app can't even start up its own web server inside of the pod. So that's like kind of an extreme example. We've gone way too low. Our pods can't start. But what I have seen in some cases is apps that are under load or running okay, but they just start randomly failing the liveness probe over time. And there's not really, rhyme or reason to it. There's just an occasional set of failures. And, depending on your different probe settings, the pod will just get killed. And so if you see that random sort of liveness probe failing or readiness probe failing, something to look at is definitely CPU throttling. There are Prometheus metrics available for it that you can get to look at percentage throttling. There's a lot of good information out on the internet. I'm not going to go in depth about CPU throttling specifically, but I'm going to talk more about just the symptoms and things. So we'll see those liveness probe failings. So what I'm going to do, obviously this is too low. Our app can't even start. And so just running through my README, I'm going to bump this up to 40 millicores. So we know it won't even start at 10. Let's quadruple that. And let's see what happens with our apps. So we have a new container coming up already. And we'll just wait. See what happens with that one. There we go. It starts running a little bit quicker this time. If we describe it, we do have one readiness probe failure. So let's see if we can get it to even start. Times 2, we may not have enough. Let me bump that up a little bit more. go to 60. All right, so we'll edit that. Go back to our pod view here. Take a look. Interesting. Usually 40 to 50 works. Dangers of a live demo. There we go. We're starting to roll through it. So our app's going to go through its rollout. We're going to get all of our pods with, 60 millicores. And just as a reference, we can take a look at where we started. And remember, we started at 200 millicores guaranteed for the app server. So we're down about 50% or more of that. Less than 50%, like 30% of that. And so we're going to see, we can keep an eye on these columns here. K9 does a nice job of showing us the percentage of our CPU requests that we're using, the percentage of our CPU limit that we're using, which those will be the same in this case because our requests and limits are the same. And then same with memory. And it'll show us our point in time memory and CPU usage. So let's wait for this to stabilize. And finish its rollout. I'm going to terminate that one. Let's see, we're waiting for readiness probes on this one. And we're pretty much in a good state. We have 3 ready pods. We have one still terminating out, but we can ignore that for now. So now what we're going to do is we're going to go back to our benchmark. We're going to run that load.js script, and we're going to see what our performance looks like. Obviously, it's taking longer than the 6 to 7 second iteration length that we had originally seen. And a little bit more background on K6. We're running 10 virtual users, as they call them, which is basically 10 tests at the same time. And I'm running 10 iterations across those, which means essentially each virtual user will run one iteration of the test. And so if we look here, our request duration is up to 1.27 seconds. Remember, we were sub 200 milliseconds before, and now we're well over a full second per request. It took 25 seconds on average to run each iteration. So our performance is severely degraded right now. In fact, with a 1 second response time, we might even be able to see it's going to take a little bit of time for things to update here. It's still working. It's okay. But if we had a benchmark of, say we wanted to keep our latency under 500 milliseconds, this would not be passing that test. We are well under that. And so as I would go look at my metrics and see that I'm probably still being CPU throttled here. And my performance is just not what I want it to be. So we're going to keep bumping that up. And we're going to go up to 150. And we're just going to see how that affects our performance. Hopefully we can start to improve that. And so at this point, you're starting to do a balance between how many pods do I want running, where should I implement horizontal pod autoscaling, and what do I want my performance to be. And so there's a lot of different factors to balance at this point, but we see what happens when we set our CPU requests too low and we run into this throttling. And then the tricky part becomes balancing. So we're going to wait for this rollout to finish again. Take a look at our pod list. Still waiting on a couple. All right. Should be pretty much there now. And we're going to rerun our benchmark. And pop that up to full screen real quick. And we'll see how long that takes. Last time, I think, it took like 25 seconds. Looks like we're moving a little quicker this time. 12, 13. We're back down to 336 milliseconds. That's a lot better. Let's see how much better we can make it. Let's edit that again. And let's go up to 400. I want to go too high because then they'll get too big to run more than one pod on a node. Remember, we only have 2 CPUs available, so 2 of those pods would be 800 millicores. Should be plenty of overhead to run these. And we can also take a look, see if our node count has stabilized out. It has not yet. Scale down takes a little bit longer than scaling up. All right. Let's start up a lot faster because we're giving them all the resources. All right, we'll rerun our benchmark here. 2, 3. Oh, we're under that 7 seconds again, and here we are back down to 162 milliseconds. But it's interesting to note that we are only at an average of 162 milliseconds. Remember, at the very beginning, we were at about 160 milliseconds. We were sub 200, and our average iteration duration was 6.5 seconds, which means the bump from 200 to 400 millicores has not really gained us anything here. And so just thinking about this app and looking at it, we're probably okay to turn that back down to 200. And this is where that, again, that CPU throttling metric can help. That percentage CPU throttled, we can see, keep that down at a very low number or add a 0 if possible, and get that tweaked. So that's the CPU throttling demo. And so if there are no questions, it doesn't look like we have any at the moment, I will forge on ahead to the third one. This one's really short and simple and easy. We've probably all seen this one. We're very familiar with it. It's the old out-of-memory kill. So if we take a look at our deployments again, and we edit it. So this symptom is when we set our memory requests and limits, our memory requests and limits too low, our limits really. So we're going to take it from 100 megabytes bits. I can't remember which one today. We're just going to call it megabytes. 200 megs down to 20. All right. And again, wait for our rollout to finish. Oh, and we see the status here real quick, flashing by on the screen. That pod was killed, because it did not have enough memory to even get started. And so that is probably the most obvious of the various symptoms that we're going to see today. The other thing to look at when that happens is if we describe the pod, we're going to see containers, Yelp app server, last state is terminated. Reason is OOM killed, exit code is 137. The exit code 137 is really important because there are situations where you will see an exit code of 137 without seeing the reason OOM killed. It is possible that the Linux kernel can kill the PID out from underneath the container, basically. And so we will see this exit code. It will always have the correct exit code, but we may not always see this OOM killed reason. So 2 things to look for: exit code 137 being the definitive, that is the answer. And so, of course, I have a bad habit of control seeing, so I just closed K9s. But this pod's going to go into crash loop back off because it doesn't have enough memory to start. So like I said, that one, the most obvious of our things that we're going to look at today. So if it tries to consume too much memory and go over its limit, it's going to get killed. And that one's really super easy to see. So I'm not going to spend a ton of time on that one. I think it's fairly straightforward. So let's get ourselves back into a good state here. We have running pods. We can double check our benchmark. and see what it says. 6, just 7. There we go. Our average duration at 170 milliseconds, iteration duration 6.4. So we're right back in that sweet spot where we started at the beginning of this. And so we're kind of back to steady state here. So we can move on to demo number 3. I'm going to, at risk of sounding like a broken record, remind everyone that the Q&A is open, and I am happy to answer any and all questions as we go through this. It's always fun if we get great questions and we can talk about more stuff here. So we talked about memory limits being too low. And now what we're going to talk about is our last one, which is one that I see a mistake that's made a lot. And it's not necessarily always causing immediate problems, but I feel like it's a ticking time bomb that a lot of us end up deploying into our clusters. And this is when we set our resource requests and limits way too far apart. And so what this does is it puts our application, our pods, into a QoS class of burstable. And this means that the scheduler is going to look at the request. So I'm going to request a certain amount of CPU, and it's going to put the pod on a node based on that request. But it's allowed to burst up to the CPU or memory limit, depending on which one we're talking about here. And it's allowed to burst up to that limit. But that, again, like I said, is not taken into account by the scheduler. So let's just kind of dive into the practical bits of that, and we can see more symptoms, and I can elaborate more. So what I'm going to do is I'm going to set the CPU request down to that 10 millicores. We know for a fact that this app uses more than 10 millicores. We showed that earlier. It can't even start on 10 millicores. But we're going to set that really low, and we're going to put our limit kind of way up high here at like 500 millicores, which we know it doesn't necessarily need all that, but we're going to do it. And we're going to do the same thing with memory. We're going to go down to 10 and 100 for the memory request and leave the limit up at 100. So this is obviously a dramatic gap, but I'm doing that to show what could happen here. So let's save that and go back to our pods. And the other thing I'm going to do is, like I said, mentioned earlier, I'm running a little bit of load here. And in a moment, we're gonna crank that up. I'm going to talk about a couple things first. So the first thing that we will notice is that we could potentially be very oversubscribed. And so I like to demonstrate this with a tool that we call Cube Capacity. It's called Cube Capacity, written by an old coworker of mine. And what this does is it puts together a really nice view where it shows the aggregate memory and CPU requests and limits across your nodes. And so we will see, and actually we have too many nodes already, so this isn't going to be quite what I wanted to see. So let's do this. We're going to also turn on horizontal pod auto scaling. We're going to turn our max replicas up to, let's call it 50. So we're going to scale this thing up. This particular problem really only gets exhibited during massive load. It only causes issues during load. So I'm going to really load this thing up. And we're going to get the deployments in the load namespace, and we're going to scale it up. To a bit more. We're up to let's go 15 replicas. The load deployment is just running that load script that I showed, but running it across multiple replicas with a lot more virtual users and potential things. So I edited the HPA in the wrong place. So let's take a look at our HPA. Max replicas up to 50. I'm going to take a look at pods again. Hopefully what we see is we're going to start scaling extremely aggressively. And the reason for this is another problem with setting your resource requests and limits far apart. Because when you're using a CPU-based horizontal pod autoscaler, which is extremely common, folks do it all the time, what we're going to see is that our target CPU usage is now sitting at 1,496% of our target. So our target is 50% CPU usage. We're at 1496. That's because it's calculated based on the CPU request, not the CPU limit. So by setting my CPU request down way, way, way low at 10 millicores, even if I'm only using 28 millicores, I'm going to start triggering scale ups. And so if we take another look at this HPA, we're going to see we're already just about to max out this HPA. So our scaling behavior is going to be all over the place. So now we have 50 pods of the app server deployment. We're still well above our target, but we've maxed out, so it's not going to scale any more up. But if we gave it more max replicas, it totally would try to do that. And then we can take a look at our cube capacity tool here. So remember, now we're running 50 pods that have a CPU limit that is 20 times the request. And if we look across our nodes, we see that our aggregate CPU limit across all 6 nodes, which we know we have too many, we're down to 5 now. We know we have too many in the first place. All of these are at a potential limit of about 300, an average of 300% of the CPU available on the node. This means that we're very, very quickly going to start approaching some serious CPU pressure across the node. If we take a look at our pods in our friend the load namespace, they're running. And so let's just run our benchmark again here and see what we've got going on. Take a look and see how our performance is. Quite likely we're doing okay right now because actually that's not true. No, we are doing very poorly. Our request duration is 700 milliseconds, so about 3.25 times our desired sub 200, and our average iteration is almost double as well. And so we're not performing super well right now. And we know, we can also pass a flag to cube capacity to see the current node usage. And so we're not hitting that massive amount of usage, but we can very easily imagine a world in which we continue to scale up here. We've well oversubscribed these nodes to their potential available resources. So let's get a little bit more extreme here. So we'll go to 30 of those. No, that's probably too many. We'll do 20. And HPA, we can edit that. Set the max to 200. All right. Keep an eye on these nodes here. You have one getting a little high. They're going to start going up here, I would imagine. And now we're up in the 600% range of potential CPU usage with 119 replicas running. And so we very quickly will scale far too rapidly and also oversubscribe our nodes. And obviously this is the CPU example that I'm really harping on here. We can definitely have this problem with memory. They will exhibit similarly to the same symptoms as we saw earlier when we set the limits to too low, because what will happen is as the node runs out of memory, the kernel is going to start finding things to kill to find room for all that memory that it needs. And it's going to do that based on priority. And we're going to see the effects of QoS class like we did earlier. But it's going to exhibit itself similarly. We're going to start seeing OOM kills in different places across the cluster. And those won't necessarily be 100% predictable depending on the topology of our cluster, what we have deployed in it, what's running in it. And then on the CPU side, as the node CPU usage goes higher and higher, the amount of throttling that happens will go up in the places that we're being throttled. And so setting those resource requested limits so far apart is just really not a great practice. Now, I understand that some workloads are burstable and need to go up in resources. I think generally, my baseline total no knowledge of your environment would be to try not to oversubscribe your nodes, via a tool like kube capacity, more than at 125% of their available resources. Another guideline is maybe to just not set your resource requests and limits more than 25% higher than your requests. And obviously you need to work out what rules there work best for your organization. And which ones work for which apps. Some apps you should be setting guaranteed QoS classes because they need all of those resources all of the time. So I think that covers the last demo. So just a quick recap of what we saw today, and then I'm going to talk a little bit about Fairwinds Insights. I'm not seeing any questions still, so please drop those in if you have them. But remember, today we were talking about the effects of bad resource limits and request settings. So the first thing we talked about is what happens when you set no requests or limits. We start to see pod evictions. We see nodes seeing memory pressure, which causes those evictions. Our HPAs don't work in that case. And scheduling is just kind of best effort and all over the place. And so that was the first demonstration. The second one, we talked about CPU throttling. If you set your CPU limits far too low, you'll see probes start to fail. You'll see degraded performance in your application. You'll want to turn those things, turn that CPU limit up in order to mitigate that. And then we talked very briefly about OOM killing, or out of memory killing, which is what happens when you set your memory limit too low and you break, and the either Kubernetes kills that pod or kills it because it's exceeded its memory limit. And then we talked about the dangers of setting resource request limits far too far apart and oversubscribing our nodes and overscaling our applications. And so, obviously there's a lot at play here. There's a lot of different factors that go into these things. And so, you may be finding yourself looking at your landscape of applications that you're running in your cluster and go, where am I going to get started setting all of this? Like, how on earth do I figure out what the right numbers are and how to set them? Obviously, these extreme symptoms we can view, but how do we set them correctly? And so there's a few different tools out there to help you with that. One of them is an open source tool that we have called Goldilocks. That's available at Fairwinds Ops Goldilocks in GitHub. And what Goldilocks does is it utilizes the vertical pod autoscaler to observe your applications and provide recommendations on what should be running in or what your resource request and limits should be. And what it does is it provides a nice dashboard to show you kind of a summary of all those vertical pod autoscaler recommendations. And so it gives you this dashboard, and you can look in your different namespaces and see what you're currently set to and what the vertical pod autoscaler is recommending. In fact, this is the vertical pod autoscaler recommending just for itself what its resource requests and limits should be. So that's one tool that you can use. And then if that, you're running a lot of clusters, maybe this dashboard isn't enough. Definitely see that a lot. Maybe you want more sophisticated recommendations that aren't provided by the vertical pod autoscaler. And this is where our software solution comes into play at Fairwinds Insights. And one significant portion of Fairwinds Insights, this isn't everything it does, and I'm not going to talk about everything it does because today we're talking about resource requests and limits, is Fairwinds Insights will give you kind of an overview of all these things and then provide recommendations. And we're using our own recommendation engine here. And this instance here has been running against this cluster that I was testing in today over the last several weeks. And so we see the names of the different pods that we're familiar with here, the different workloads. We have that app server that we've been looking at. We also have our DB. And so if we click into this, we can look at the database and see this graph that's super useful of the last, 2 weeks of data. And so we see the maximum, the average, and the minimum usage over this time. And then we also see this blue line. We see what we currently have set. Remember, we started out with 200. This is on the database. We have 200 megabytes or megabytes. And we see here we can actually drop this down a little bit. We can drop this down probably fairly safely to this 159 megabit place and save a little bit of money. And so we have some cost calculations that go into that. We can also do this for CPU usage. Turns out for CPU usage, I am right on the money here. That was probably by design, but I have tweaked this. And over this time, we've really been sitting in a good spot here. And we can do that for each of our applications in here. And then we can also specify like the different QoS classes that we want to see. So we can say this app really doesn't need to be in the guaranteed class. Give me a recommendation that is burstable. And we can change that and it'll start to give us recommendations for resource requests and limits that are separate from each other. And then again, we're tying that into some cost information so that you can see that here. So insights can definitely help you. This could run across multiple clusters. So you could be seeing this for every cluster you have up here, and super useful tool for doing that. So that's my spiel for today. If we could pop up the last polling question. I think we have one more question to ask y'all, just so we can get an idea of where y'all are at. So where are you at in your Kubernetes journey? I'm learning about containers in Kubernetes. I'm planning to use Kubernetes in 6 to 12 months. I'm only using Kubernetes in testing and development environments, or I'm using Kubernetes in production. Let's see what y'all have to say. Getting a few responses. So far, the majority of people planning to use in 6 to 12 months, but we also have quite a few folks using it in production. Lots of people using it in production. It's been fun to watch the trend of this particular question over the last year and a half, 2 years, because 2 years ago, it was pretty much everyone was in those top two categories. And we've definitely seen much more of a shift down to the bottom. More and more folks using it in production these days. So appreciate your responses to that. And I'll give you all a few seconds to ask any last minute questions, and then I will hand it back to Cody.
So while we wait on those questions to potentially come in, let's go ahead and give away some gift cards. So these are for 4 $25 Amazon gift cards. Our first winner is Walter H. Our second winner is Carlo V. Our third winner is Maria N. And our fourth and final winner is Elias A. So keep an eye on your inbox to claim that gift card. And if you don't see an email, just check your spam folder. I'll also take this time to remind our audience that the session was recorded. So if you missed any of our demo today, you can rewatch it. The on-demand will be living on the DevOps website, and you'll also be receiving an email shortly after we conclude the webinar today with a link to access that on-demand. So Andy, I'm not seeing any more questions. Are you seeing any come in?
I am not. Well, thanks everybody for attending today. I super appreciate you all listening, and have a great rest of your day and week.
Awesome. And Andy, thank you so much for putting together this demo. I know how much we all love watching demos. It's more than just a slideshow. So a lot of work went into this presentation. I really appreciate it.
Thanks.
I'd like to thank Fairwinds for sponsoring today's webinar. And my final thanks goes to you, our audience. We really appreciate you joining us today. Take a second to fill out our post-webinar survey. It should pop up on your screen right after we close out of this webinar. And we hope to see you in the future at a future TechStrong Learning webinar. This is Cody J. Brown signing off.